Welcome to another video on the Single Agent Search website and Moving AI, the demos that are available there. The demo we're going to do today is A-star running on a graph. And if you've seen the A-star or the Dijkstra's algorithm running on a graph, this is going to be similar to that one, but a little bit different. So the first thing I'm going to do is just run through some of the functionality we have, the different options we have at the bottom here. And then we'll look at these algorithms, and then we'll talk about some of the tasks that could be done here. If you're teaching the class, that you could use these for helping your students out, or if you are just wanting to learn and make sure that you understand these sorts of algorithms well, then you could do that as well. Okay, so we have nothing in the graph right now, but basically we can choose what mode we want to be in. So right now we're adding nodes. So when I click, we're going to get a node in. That doesn't give us edges, so I can now add some edges here and get some topology of a graph. And then I can move nodes around. And something that you'll notice that's different between the Dijkstra's algorithm, or the Dijkstra demo and the A-star demo, is that now we see that I actually don't have ability to change the edge cost, but as I move nodes, the cost of the edges changes. So this is a 2x2 square here, is how the coordinates are laid out. So if I'm going from one side to the other, my edge will be about cost 2. And anyway, so we see the costs here set accordingly. And then there is a default graph that you can start with that is just there if you don't want to have to build a graph yourself. But we could clear that and start over if we wanted to. Okay, so this is how it works, and then this is in terms of building the graph. Then we can also say we want to run a different algorithm. So I can choose an algorithm. Choosing an algorithm will move into this find path mode, and I can now choose the start and the goal, and I can step the search. And as I step the search, I can watch how that search runs. I can do that with A-star, and we see different behavior. Weighted A-star in this case is going to have the same behavior. In fact, if I'm doing the same problem, I don't need to select it again, but we see the same behavior there. But we'll talk more about that in just a minute in the video. Okay, so this is how things work here, and now what we want to think about is what are some things that we can learn from this, and what are ways that we can test our knowledge and our understanding of algorithms. The first thing that's really helpful to do is just to look at these problems, and we have all the nodes that are in the search space here. So A, B, C, D, and E are here. Their current status of being open, closed, or generated. Their G and H cost, G cost, if only if they've been generated within the search. And then we can also see what's currently on the open list, what's currently on the closed list. The goal is drawn in this pinkish color. The next node on open is drawn in yellow. And nodes that have been expanded are drawn in more of a red color. And the open list then is either green for states that are not going to be selected next, or yellow for states that will be selected next. And then we can see what's on the open and closed here. So this is really useful for taking an example and just stepping through step by step and saying, do I understand how this algorithm works? Do I understand what it's going to do one step at a time as I run a particular algorithm on a problem, and verify that I'm calculating my G costs and my H costs properly. Given that on this problem, the H costs are, we don't necessarily know what they are because we need to be able to estimate distances. Then here they're written down here so you can do the calculation. Notice also in the Dijkstra's algorithm demo that it'd actually be hard to come up with H costs there. And so this is actually a first question here. I should say this the other way around. Why do I have it so that in this demo you move nodes and the edge costs change, where in the other demo I could set the edge cost to have any cost that I wanted? And when we think about distances within a state space, then it's actually very easy to estimate distances. If this is now a planar 2D plane, and I'm putting points within that 2D plane, then I can use distances within that plane as estimates of, like straight line distance is always on a Euclidean plane. Straight line distance is always going to be the shortest path between two locations, and so that's going to be an admissible heuristic for distances. If I just have a graph with arbitrary edge costs on it, then I'm going to have to find a way to get a heuristic from that, and that's a bit more complicated even to show. We do have some other demos on this page on the FastMap algorithm and the differential heuristic. There's also ALT, which is A-star landmarks in the triangle inequality. It's designed for directed graphs. It's very, very similar to the differential heuristic. Actually came before it. So you can find those, which would tell you how to build heuristics on graphs with arbitrary edges on them. But if we are just sitting here in a space like this, then we're going to just use straight line distances. So that's why we do that in this demo, and it makes it a lot easier to work with. The next thing, just in terms of understanding the algorithms, this is something that applies both to the Dijkstra test problem and to A-star, but it's a little bit different to do it here, is this question of, if I'm implementing this algorithm and watching it run, what I'd really like to see is I'd like to see the search generate a node with a cost that is too high, and then come back and generate it again with the correct cost. So I can see the parent being updated on the open list. And if I step the search here, you're going to see that, that actually every node has as its parent the first state that generated, I think. Actually, we could double check D. D came from C. Yeah, that's right. Now, there might be a slightly shorter path through here, but actually we terminated our search. But the question is in general, and if we clear the graph, can we create a problem, maybe even a minimal problem, where the so if we think about the shortest path from the start to the goal, so I'll go ahead and add some nodes here. So we've got a start, we've got a goal here. And what we want to do is create an example around here, basically a minimal example, where the shortest path will be generated first suboptimally, and then later will be updated to be more optimal, or to be actually optimal. Okay, so I'll say that again. We think about we're going from the start to the goal, in this case A and B, and what we want to see happen is that the shortest path, so let's just put a path here, and we can have some edges here. Okay, we do something like this, and if I do find a path, let's use A-star, and we step our search, what's going to happen is, of course, it comes down here, and it finds the path from the start to the goal. And the question is, what can we do to make it so that some of the nodes on this path are going to be generated with one cost, and then generated again, or with the correct and optimal cost. And by drawing this in this way, maybe I've already given some hints of how to do this. But what we can do is, if we put a node right here, so this is about understanding the behavior of A-star. A-star is going to go towards the goal, which means A-star is always going to generate a node like E before it tries to go down this optimal path, because this looks like the straight line path to the goal. But if E in the end only takes us to D and doesn't take us to B, then what will happen is we'll generate E and we'll generate D, and then we'll come back through C and find the shorter path. And this is a minimal example. I mean, we could make, even if we made D the goal, then A is always going to try and go through C to get to the goal. So if we want to have this, we need a node in the way that's basically preventing the optimal path from being fully generated. And then we have some suboptimal path that has fewer edges in it. But actually, in this case, it doesn't have fewer edges. But what it does is it gets us to look like we're going straight to the goal, and then causes us to go back to D. Okay. And these sorts of examples we'll see again when we get to, anyway, some other things you'll see, or if you go look at the lectures for the class, you see this when it comes to inconsistency. Okay, so if I do this now and I run A-star, so same start and goal, and we step the search, what will happen is we generate E. We're going to expand E because E's got this really low F cost, because it looks like it's going to go straight to the goal, where C is a bit higher. But when I step the search, then hey, I discover that E doesn't go anywhere except D. Now D has got a cost of 3.16. I step the search, and hey, I've updated it from 3.16 to 2.42 via the path from C. And now I'm going to come down here and I'll find this shortest path. Okay. When I'm doing it here, it can seem it's really easy, but I'd encourage you to, of course, if you're doing it for a class, then you can ask the class to do it without showing them this video. But I'd encourage you to, come back in 24 hours and try it again and see if you can do it as a test of really understanding. So another interesting question we have here is this: we have these weighted A-star algorithms. So weighted A-star is going to prioritize the states with lower heuristic because the F cost is F equals G plus W times H. So when W's 100, then we're really looking for a much higher, or much lower H cost. A little bit of difference in H cost is going to give a much lower F cost overall. And so there's an interesting question here where we can ask. So we're going to, again, on this problem, we're going to be thinking about finding a path from A to B. And if we watch what happens here, we do this normal thing where we're expanding E, and then we discover there isn't a good path there, and then we come back through D. And so another interesting question we could ask here on this example is, what do I have to do to cause the shortest path not to go down this outside area here, but so that we could just go A, E, D, and B? Because the difference in the path here, weighted A-star of a weight of 100 actually can be 100 times suboptimal. So there's no reason why it can't actually go find this path A, E, D, B. That's still within 100 times of the optimality bound. But for some reason to think about is it's still actually finding this optimal path instead of the suboptimal path, which could have been less work. And so if we think about this, then we need to think about why is it expanding C and why is it expanding D? Okay, so I'll give you a second to think about that, or you can pause the video. But if we look here, A, C, D, what we can actually look at is what the H cost is. So the H cost of C is 1.04. The H cost of D is 1.11. And what that means is that when I look at expanding D, D times 100 is actually going to be 111. And D times, the value of C, which is 104 times 100, is going to be 104. And so C is going to have a lower F cost than D will. So we'll do C before D. However, if I move my nodes, and I'm just going to bring, now this doesn't update dynamically here, but if I move my nodes over just a little bit and make it so that the distance from B to the goal is slightly less than C to the goal. So let's go ahead and reset to run weighted A-star here again. So now we see D is 1.00, C is 1.04. Now when I run weighted A-star of 100 and I step my search, I do E as normal, but now I'm going to continue from D to B and I'm going to get this path here. So it's just a subtle difference in H cost between C and D that governs the behavior of whether I can find the shorter path on the bottom, or where I find the longer path, but I stay greedy and do one less node expansion, or whether I continue and do C on the top. Now related to this is an interesting question of, can we create a problem where we actually see that weighted A-star does more work than A-star does? Normally we think of A-star, in this case we saved one node expansion. We think of like weighted A-star saving us some work because, for instance, we might have some obstacles, but we can go around those obstacles in a greedy way. And so weighted A-star. There's another demo of A-star and weighted A-star on a map, and you can look at those and see when you compare them that weighted A-star tends to do much better than A-star does. But here we can really create adversarial in problems, and so there's an interesting question, which we've had some hint with that problem we just looked at, of whether we can create a problem where A-star does much better, and even Dijkstra's algorithm does better than weighted A-star, let's say with a higher weight. So again, I encourage you to try and do that, because doing that on your own is really, really informative. Right? This is how you test if you understand what's going on. You can watch the behavior and get a deep understanding for the behavior of these algorithms. But I'm going to assume if you wanted to do that, then you've paused the video and looked at that, and let's think about how this can happen. So here we're going to put the start. On the outside, we're going to put the goal here. And if you remember from the example we just did, we really care, especially when I put a weight of 100, we're really going to care primarily about the h costs, much, much more than we care about the g costs. So the idea here is that the optimal path to the goal is going to start from A, it's going to go out to some state that's farther away, and then it's going to go back to the goal. So put that a little bit more in the middle right here, and this is what the optimal path looks like. It goes out there and then comes back down here. And then what we're going to do is we're going to create another path here that goes around the side. And this path, we're just going to put a bunch of nodes here. So this path is getting closer and closer to the goal. And so we made this really small, but we'll get to see this behavior. And so what we see is we have a path here where the heuristic is staying relatively small, especially compared to the heuristic of this state out here, which is the state we have to go to get to the goal. And let's go ahead and do let's do an A-star search to begin with. So what is the A-star going to do? Well, we step the search and it generates both of these. It's going to start going around this path here. And at some point it generates a path that's long enough that says now we should come back and try this alternate path to the goal. And it's still saying here that you know, at some point you could still keep going this way and say maybe if I went straight line here it'd be faster, but at this point we've said hey, we're going to go out here. So what we see is A-star did A, D, E, and F, or actually got to F, it didn't expand F before it proved that this was the optimal solution. But let's watch what happens with weighted A-star weight of 100. So what's happening here now is because all of the heuristic values here are smaller than C is, and we're multiplying this by 100, that we're basically just going to keep stepping the search around this loop here until we come to B. And so weighted A-star is actually going to find this very expensive, but weighted A-star is what's called a satisficing search. That is, it's only looking for a path that satisfies this bound. It's not trying to find, it's not trying to do optimization. It does implicitly do some optimization, but it's not explicitly, we're not explicitly, it doesn't care. It just says as long as they get one that's within a cost of 100, then I'll be happy to return that solution. And then it never actually goes and does this path here. Now, if we do weighted A-star of 2, we can step this search, and I don't know for exactly these numbers. What we see is that we come along here further, but because our weight is only 2, then eventually it will stop along here and then go and do the find the optimal path. But when we do a high enough weight, then we actually get to go all the way around the cycle, and weighted A-star does much, much more work than A-star would do, or even weighted A-star with weight of 2, or even Dijkstra's algorithm. So if we step Dijkstra's algorithm, in fact, Dijkstra's algorithm is going to come here. It did one more node than A-star did, but still doesn't really compare to what's being done here. Okay, so that concludes the demo here. We've seen that we can use this to create a graph. We can, the edge costs are set by the location within the world. And so we can create those nodes, we can move them around. And then we looked at how we could understand what's going on by looking at Dijkstra, A-star, weighted A-star, running on these problems. We can look at how we do reopenings. We can look at when weighted A-star is going to find a longer path versus a shorter path, and some of the different variants of that. And all of this you can do, you can see the entire open list here as you run. So this is good for debugging numbers and things like that. Thank you very much for watching today, and we'll see you in the next video.